Math 2414, Trigonometric Substitutions, Video 8. One more type of trig substitution. So far, we've developed a technique for integrating something of this form, something of the form a squared minus x squared, which was x equals a sine theta. We've come up with a technique for integrating something of the form the square root of x squared plus a squared. That was x equals a tangent theta. And just a reminder that we also developed various techniques for dealing with the fact when the coefficient of the x squared was something besides 1. But the one bridge we haven't crossed yet is what happens when we are trying to integrate something of the form x squared minus a squared. And you might think it's the same as the top one, but it's not. The reason it's not the same as the top one is because the motivation behind the top one was using 1 minus sine squared theta, because our constant was on the left side of the subtraction problem. Here the constant is on the right side of the subtraction problem, not the left side. So we're going to have to use another Pythagorean identity that has a subtraction problem with the constant on the right side of it. What would that be? Well, let's find out. I've got an integral involving the simplest type of square root that's going to prompt this substitution. The integral of the square root of w squared minus 1 is, the integral of the square root of w squared minus 1 dw. Again, our motivation is to try to find a trig identity that will allow us to collapse this binomial down to a monomial, 2 terms to 1 term. So we want a trig identity that one side of it contains something minus 1. That trig identity, secant squared theta minus 1 equals tangent squared theta. So in order to take advantage of this, we need to take our subtraction problem, w squared minus 1, and since the constant parts match, we're just going to equate the variable parts. We need w squared to become secant squared theta. So if we square root both sides, we're going to get w equals secant of theta. I'm sorry, that second to last equal sign is bothering me. It is so poorly drawn. But we need w squared to equal secant squared theta in order to take advantage of this identity. So we need w to equal secant theta. So let's run with that and see what happens. If we let w equal secant theta, we have to do the same 2 things we've done before. Number 1 is to differentiate this to get dw equals the derivative of secant theta is secant theta tangent theta. That's calculus 1 knowledge you need to just know. We also need to draw a picture of theta to use when we undo the substitution. Secant is a reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. We need hypotenuse over adjacent to equal w. So if we put a hypotenuse of 1, a hypotenuse of w and an adjacent side of 1, then cosine of theta would be 1 over w, so secant of theta would be w over 1, aka w. We have the correct setup, and please forgive me, I meant to write those in blue. Doesn't really matter, but trying to be consistent. And in anticipation of using this triangle later, if we did the Pythagorean theorem to find the opposite side, it would be the square root of w squared minus 1, which not coincidentally matches the integrand, with the square root in the integrand. All right, so let's do all this. If we let w equal secant theta, then our square root becomes the square root of secant squared theta minus 1. And dw is secant theta tangent theta d theta. All right, let's go to town on it. Starting with the square root of secant squared minus 1, well, let's just simplify it real quick, because the more of these you do, the quicker they get simplified. We chose our substitution because secant squared minus 1 is tangent squared. So this becomes the square root of tangent squared. But the square root of tangent squared is just tangent. So we have a tangent, secant, and another tangent, which means we have a tangent squared theta, secant theta, theta. All right, now that we've got this, we have to decide how are we going to integrate this. Let's see. We have rules for tangents and secants, but none of them apply here. If the secant has an even power, we use a substitution of the tangent. But the power on the secant is not even. If the tangent has an odd power, we use a substitution of u equals secant. But the power on the tangent isn't odd. So all of that fails. So what are we going to do? Well, we could try turning everything into sines and cosines. Let's see what that does. Now let's just talk it out. Tangent is sine over cosine. Secant is 1 over cosine. So this would become sine squared from the tangent squared. But on the bottom, we would get cosine cubed. Could we do something with that? Well, we could change sine squared to 1 minus cosine squared and go down that path. And looking at it, I do see a path to the end. But I'm going to take a slightly different path. I challenge you to change sine squared to 1 minus cosine squared and see if you can take it from there. I would split it into 2 fractions and see what happens. But I had a second train of thought prior to writing that. Now, some people's comfort zone is sines and cosines, but they would rather not do fractions. Another thought is there's a tangent squared, and I know a trig identity that involves it. Tangent squared is equal to secant squared minus 1. Is this something we can take advantage of? Yes, if we distribute. Because if we distribute, we get the integral of secant cubed, which I know the answer to, minus secant. I also know the answer to. Now, you may or may not have both of these answers, but that's okay. As long as you find a path to the end, you're good. I warned you back in week 2, video 8, that the integral of secant cubed was one of those integrals that just shows up. Integral of secant just flat out needs to be. But let's just assume that we know the answer to both of those from previous integrals and write that on the next page. Oh, Nelly, look at all that. The integral of secant cubed from a previous video in this series and from video 8 in the previous series is 1/2 times the quantity 1/2 times the quantity secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. Just realized I left off the end of the absolute value, so let's draw that real quick. And draw a straight line from there. And close off the parentheses that was opened right after the 1/2. And the other side of the subtraction problem over here is the integral of secant of theta, natural log of the absolute value of secant theta plus tangent theta, and of course plus c because it's an indefinite integral. Okay, so now we undo all the thetas. Well, we could, but look a little bit more closely from an algebraic perspective. We have some like terms, namely this guy and this guy. And it looks like they cancel because one's positive and one's negative, but they don't because the first one is trapped inside of parentheses with 1/2 in front of it. So in order to gain access to that first natural log, we would have to bust it out of parentheses by distributing. Then we can combine like terms. So why don't we do 2 things? Distribute the 1/2 and combine like terms. If I distribute the 1/2 to the first half of the parentheses, 1/2 secant theta tangent theta. And if I distribute it to the second half, then it picks up a 1/2. But when this picks up a 1/2 and we combine it with this guy, we have to do 1/2 minus 1. 1/2 minus 1 is negative 1/2. We end up getting this. If you have any friends that are in pre-calculus or anywhere before calculus 1 and plan on taking calculus, please tell them the following. Calculus is easy. It's the algebra and trig that will murder you. I'm not kidding here. All right, so, well, metaphorically, I've never heard of trigonometry jumping off the page and physically killing anybody. But I digress. Let's review what's happened so far because it's been a lot. We had a fairly harmless looking integral. We chose the substitution of w equals secant theta because it collapsed the binomial to a single term that we square rooted. And we ended up with the integral of tangent squared secant theta d theta, which did not fit nicely into our secant tangent rules. So we can fiddle with it, but by changing tangent squared to secant squared minus 1, we ended up with two integrals that we had seen previously, the integral of secant cubed and the integral of secant. And their answers were at the top of that. And then there was a couple of like terms we could combine only after distributing the 1/2. Now we got to undo the substitution, and at this point it's actually not that hard. It's the easy part of the problem. Remember, undoing the substitution involves the triangle that we had earlier, the picture of theta, and that triangle had a w here on the hypotenuse, one on the adjacent, and the square root of w squared plus 1, square root of w squared minus 1 for the opposite side. That w is bothering me. W squared minus 1. That one's going to bother me, so is this one. You know, being OCD or self-diagnosed as OCD can drive you crazy. All right, so let's pull off all these substitutions. We basically need to know what secant theta and what tangent theta equal. And in this picture, secant theta was w. That was our substitution way back here. Secant theta was w. So we really don't have to rediscover that. But at this point, they probably might have forgotten it. Let's go ahead and write that. Secant of theta is equal to 1. W. What's tangent of theta? Well, opposite over adjacent, which is just the square root of w squared minus 1. So actually, our answer isn't going to be too terrible. 1/2. Secant of theta is w. Tangent of theta is the square root of w squared minus 1. Minus 1/2, natural log, absolute value. Secant of theta is w. Plus tangent of theta is the square root of w squared minus 1. Plus c. And that would be our answer. The nauseating answer? Of course it is. But maybe it's not the color I wanted. Maybe you'll start believing me now when I say that we are at the pinnacle of difficulty. At least I think we are. I think once we get past this section, things are getting a little bit easier. I'm not saying crazy easy. I'm saying easier. Let's try one more example, and then we will categorize this technique.